Alright, in this video we're going to take a look at soil characteristics. We'll start with an overview of agriculture and soil science fundamentals. So a definition for agriculture might be a little bit more broad than you're used to. The practice of cultivating soil, producing crops, and raising livestock for human use and consumption. Sometimes we forget about the raising livestock part. This can be done on 38% of the Earth's surface. Croplands, meaning the growing of plants, and we only have 11% of our Earth's surface that we can grow plants on, and right now we're maxed out at that level. Rangelands, also called pasture lands, are where we graze animals, and 27% of our land is being used for that. What's the world soil conditions like? Soils are becoming degraded in many regions. Here we can see areas that are green that represent stable soil, and these are areas where the population density of humans is very low. Areas of some concern are in orange, and we definitely get a lot of Western Europe. Almost all of Western Europe is either some concern or serious concern. And we also we see a lot in Africa here, some serious concern areas. And then we have non-vegetated land like on Greenland. So which continent is the worst off? In general, we say that Europe's soils are degraded the most because of a long history of intensive agriculture. This is where we've been farming intensively, meaning using fossil fuel-based machinery and fossil fuel-based fertilizers for a long time. But Asia and Africa are catching up. Causes of soil degradation. Well, we have a few things going on here. The biggest one we can see is overgrazing, meaning that we don't give the vegetation long enough time to regrow. And we also have deforestation. And with deforestation, we get a lot more a lot more erosion occurring when we have storms, because the runoff is flowing so fast that runoff water picks up the dirt and carries it to the nearest waterway, creek, etc. And then we have cropland agriculture, where we're just saying that some of our current practices are not being sustainable, and so we're seeing soil getting degraded as a result. And we'll learn more about that in a future lesson. A little overview of the origins of agriculture. So the Fertile Crescent along the Tigris and Euphrates River, that's a big area. China has been doing agriculture for a long time. Mesoamerica and the Andes. And to our knowledge, agriculture developed independently in all these areas. And you can see some of the different foods that they used. Wheat in the Fertile Crescent, rice in China, corn and squash in Mesoamerica, and potatoes in the Andes. So when do we think that agriculture really began? Well, hunter-gatherers for a long time, so maybe 12,000 years back. Traditional agriculture being somewhere around the last 8,000 years. And what we call industrial agriculture, as you see in this image here, in the past about 100 years. So traditional agriculture is agriculture by muscle power, animals, hand tools, simple machines. And subsistence agriculture is when the family produces only enough for itself. Or intensive traditional agriculture is where the family uses animals, irrigation water, and fertilizer to produce enough to sell at market. So intensive traditional, we're going to contrast that with intensive industrial. Industrialized agriculture is modern intensive agriculture that demands that vast fields be planted with single types of crops. The big difference here is that we're using machinery, fossil fuel-based machinery, and so depending on what kind of crop it is that you're cultivating, you have to use a certain type of machine for that. So you really cannot easily combine different crops. And there's a lot of problems associated with this, as we'll discuss in class, and some which we learned about already. But think about this farm field. It is hundreds, perhaps even thousands of acres large, and it is has a species richness of basically 1 in terms of plant species, and a evenness of complete dominance. So this, as an ecosystem, it's extremely limited, and it's not going to be providing for providing habitat for a variety of insects, birds, and mammals, and everything else. So this is what we call monoculture. It's the uniform planting of a single crop. And the Green Revolution we'll talk about later in this unit. It's an intensification of industrialization of agriculture, which has produced large yield increases since 1950. And this gives increased yield per unit of land farmed. So because of this revolution and the use of mostly synthetic pesticides and fertilizers, those two things together have allowed us to get a lot more yield per unit of land per acre. And it began in the US and other developed nations. The techniques and chemicals were exported to developing nations like India and those in Africa. But what we're going to see is that it has a lot of detrimental impacts on the land, as we'll study in a later unit. Soil as a system. We've already been exposed to this through the video we watched, but soil is a complex mixture of biotic and abiotic factors and organic and inorganic compounds. So for example, what we call humus, and that would be an organic component, and minerals, which would be inorganic components, minerals being like iron. And so just a little artist's rendition of all the different things we have going on here. Snails on the surface, bugs creating some channels in the soil which help bring oxygen. We have a cicada nymph here. Earthworms are especially important for not only breaking down organic matter because they're detritivores, but they also provide those channels for oxygen. And we have soil fungi, again, with the job of breaking down dead organic matter back into soil nutrients. Mites, and then beetle grubs, and let's not forget about the other microorganisms, the bacteria. And some of these bacteria are essential for providing nitrogen to the soil. And we also have protists. They're another category of microorganisms. Let's take a look at soil formation. In this cutaway section, we can see that there are different layers within the soil. All soil starts as rock, and here we see granite bedrock. And that rock is what we call the parent material. It's the starting material that breaks down into soil. And this can be bedrock, the solid rock that makes up the Earth's crust. It could also be freshly formed igneous rock from a lava flow. And it affects the resulting soil, or produces the resulting soil. Well, it affects what you get as the final soil. For example, sandstone bedrock transforms into sandy soil, and that's what I have around my house. So the process of the rock turning into soil is what we call weathering. And it occurs by physical weathering, chemical weathering, and biological weathering. With physical weathering, this is where force comes into play. So wind, rain, these are all factors that can actually exert a force to break up the rock. Thermal expansion and contraction is a big one. As that rock heats up, it's going to expand a little bit. As it gets cold, it's going to contract, and that over time can loosen up the rock. And then water freezing. If you have water penetrating some of the pores in the rock, and then it freezes, as it freezes, it's going to expand and just bust open that rock. Kind of like if you ever put a can of soda in the freezer and forgot about it. Chemical weathering is happening also, and gases in the atmosphere, like oxygen, can begin to combine with the minerals of the rock to form oxides. And sometimes those oxides are not as strong as the original mineral, so they're more prone to weathering. And another good example of this is when you have carbon dioxide in the air, which combines with water, and it makes the water acidic. It turns it into what we call carbonic acid. And that carbonic acid can begin to dissolve away the rock into minerals that will become part of the soil. And we also have biological weathering, and this would be tree roots that can go into little breaks in the rock and bust it apart. And we also have lichens, which can establish themselves on the rock, and as they grow, they can continue to penetrate into small pores on the rock. And so this is the part of the process of rock becoming soil. Once rock is broken up and we have soil, we have another process that can occur, which is erosion, which is the movement of soil from one area to another. So if you have soil in an area, it could be because of weathering of rock to produce the soil there, or it could be because erosion brought soil from somewhere else to that area. And what we see in here is, number one, we see a little gully where water flows through quickly, and that can cause fast erosion. And we see here an evidence of where this soil level used to be, and then that soil level has dropped as it's been eroded away. Soil profile explains to us or describes how different layers in the soil compare to each other and what their different properties are. These layers are called horizons, and in the simplest model of this, A is called your topsoil, and it's just the dirt that you see on top. B is the subsoil. C is the parent material. But there are other areas that we throw in between the A and the B, in between the, and under the C. So most also have O, E, and R. Okay, so in the simplest, topsoil, like I say, that's the dirt on top. Subsoil is underneath where it's starting to get a little bit more rocky. And then C, your parent material, that would be like when you dig down deep enough that you basically just hit rock. But let's take a look at the O, E, and the R. O horizon, O stands for organic or litter layer. For example, decaying leaves. And the A horizon, the description of that is it's the topsoil. It's mostly inorganic minerals with some organic material and humus mixed in. And this is crucial for plant growth. So humus is what we get when the stuff in the O horizon is beginning to decompose. And so it gets kind of wet and slimy. The E horizon is between the A and the B, and it's called E for eluviation. And this means a loss of minerals by leaching, which is a process whereby solid materials are dissolved by water and transported away. So you have minerals in the A layer which can get washed away, and when they do, that becomes an E horizon, E layer. And in the B horizon, this is also called the zone of accumulation, or deposition of leached minerals and organic acids from above. So whatever chemicals have gotten leached from the E horizon, they end up in the B horizon. And one way that I remember it is E, I think of exit, because that's where the minerals are leaving. And then the C horizon is a slightly altered parent material. And R horizon is bedrock. So here's a diagram that kind of shows it nicely. So here we see some organic matter on top, twigs and things like that. And then we get into the A horizon where we have minerals and organic matter. So we still have some organic matter in there, but it's in the process of decomposing. And the minerals, we can roughly say that we have strong minerals here because we see it as a darker color. Roughly we can say that. And here we have the E horizon, which is where we're seeing mineral depletion. It's lighter in color. And underneath that is where some of those minerals would have accumulated as they get carried down by the water. So this would be the zone of accumulation. And then down here we see more rock. And that humus we talked about is mature compost, what is left when organic matter breaks down. And it's somewhat spongy. It helps soil to retain moisture, nutrients, and oxygen from microbes. And it's dark to the carbon content. And it is a really key component to healthy soil. We'll learn that one of the best things you can do to improve the fertility of your soil is to add organic matter. So let's talk a little bit about soil characterization. We can have clay, peat, chalk, and silt. These are all different components of soil. And we describe soil in terms of its texture, its structure, and its pH. So the texture is determined by the size of the particles. And there are three main categories. We learned this in our lab. Clay particles are very small, about 0.02 of a millimeter. Silt particles are anywhere from 10 to 20 times bigger than that. And sand particles are as large as up to about 2 millimeters in diameter. Sand particles are ones that you can still see relatively easily with the naked eye. And the best for general plant growth is loam, which means an even mix of these three types. And they all have functions. So a soil texture triangle, we'll learn how to interpret this in our lab, but it is just showing how the different proportions of these three create different types of soil. Soil structure, sometimes people say it's the same as soil texture, but this is more of a measure of the clumpiness of the soil. In other words, how well is it holding up together? The structure of the soil would be like, does it have a lot of pores for oxygen and things like that? The pH of it is the degree of the acidity or alkalinity, which influences the soil's ability to support plant growth. Low pH soil is called acidic, high pH is called alkaline or basic. And it's mostly determined by the type of bedrock that formed the soil. For example, limestone will turn into alkaline soil. It is also influenced by rainfall and the type of vegetation. And each type of plant has its preferred pH. So blueberry plants, for example, like low pH, acidic soil, and asparagus plants like high pH or alkaline soil. Let's take a look at the Amazonian rainforest soil. So here we have a very thin topsoil and lots of rain, which leaches nutrients from the topsoil down and out of reach of plant roots. So you don't see a very thick topsoil, and you pretty quickly see that zone of alluviation, the E layer. And nutrients not leached are taken up by lush vegetation, leaving little in the soil. And when farmed, this soil gives out after a few years. So in the rainforest, because it's raining so much, a lot of these minerals are getting washed through the soil. And to help prevent the loss of those nutrients, as an ecosystem, you have the plants that are growing quickly from that soil. So whatever decomposition you have happening in your O and your A layer, those nutrients are pretty quickly getting taken up by new plants, so that they're not lost out of the ecosystem. So decomposition happens extremely fast in the rainforest because it's warm and it's moist. So most of the nutrients are actually in the vegetation itself, not in the soil. But this is very different from a Kansas prairie soil in the grasslands area, where you don't get much rain, and the topsoil is rich and productive. The low rainfall keeps nutrients in the topsoil, where plants take them up and recycle them back into soil when they die. The rates of decomposition are slower here because of less rainfall, and it's also usually a bit colder. And so you have thicker layers of the A, and you don't see the E layer until you go further down. So a little introduction to a term here. It's called swidden or slash and burn agriculture. This is when a tropical forest is cut and the plot is farmed for 1 to 2 years, and the farmer moves on to clear another plot, leaving the first to regrow into forest. And this is commonly seen in developing countries. And it can be sustainable if it's not done too quickly, where by the time they get back to the first area that was cut, if that soil has had a chance to regrow into forest, then that process can be repeated. But if the population density is too high, then there won't be enough time for the regeneration in between rotations. Let's talk about floodplains for a moment. This is where we find some of the richest topsoil, and for the reason that floodplains have nutrient-rich soil because periodic flooding deposits new soil, renewing nutrient levels. So whenever there's a periodic flood that might happen every 10 or 100 years, the river can overflow its banks, going into the floodplain, the flat area next to it, and it will leave behind some of the sediment or dirt that it's been carrying, and that would have been brought or picked up a long way back from some other area. So basically you're taking an area where you may have been farming, and if you've been farming there for a while, the soil may be getting depleted of nutrients, but then that flood comes along and deposits new soil with new nutrients from areas that haven't been formerly farmed. So it's a great way to renew the nutrient level of your dirt. And so when we think about the Tigris and Euphrates River, some of those birthplaces of agriculture were along floodplains. But because we're doing a more control of our waterways nowadays, trying to control flood, because they do cause damage. They can cause property damage as houses get flooded. So because we try not to let this happen as often, it is impacting the nutrient levels of our soils. And that's where I want to stop here. So I'll see you guys in class.